Hello, and welcome to the second webinar in our Fatigue Testing of Metals series. Today we'll be hearing from Dr. Erik Schwarzkopf, Senior R&D Engineer and Staff Scientist here at MTS Systems Corporation. With more than 35 years of experience in materials testing, metallurgy, and systems engineering, Dr. Schwarzkopf is widely recognized for his leadership in testing techniques and is looking forward to sharing some of his knowledge and expertise with you today. Before we get started, here are a few housekeeping items to keep in mind. First, we are recording this webinar and we'll share the recording online at a later date. You will receive an email notification once the webinar series is posted. Second, we will address questions at the end of the webinar. You may submit questions at any time through the chat function, and we will address as many questions as time permits after Dr. Schwarzkopf's presentation. So now I'd like to turn this webinar over to Dr. Schwarzkopf to discuss the fatigue testing of metals.
Thanks, Andrea. Last time we talked about, 2 weeks ago in the introduction, we talked about how things change from a strength-based design criteria to a cyclic stress-based design criteria, then to a cyclic strain-based design criteria, those being the important parameters for determining failure. Today we're going to talk about the details of LCF and HCF, LCF being low cycle fatigue and HCF being high cycle fatigue. We're going to talk about how to generate the command. We're going to talk about how to collect the data. We're going to talk about how to know when the test is finished. We're going to talk about how to restart an interrupted test. And we're going to talk about how to check if things are going to work before we start. There's no way to know exactly how things are going to work, but there's an idea about a sanity check for the system. So let's get going. This first slide is very wordy, but we're going to talk about command generation, control mode, end levels, frequency, and wave shape. We're going to talk about data acquisition. Generally, it's peaks and valleys and hysteresis loops. But we're not going to store every cycle because some of these tests are 10 million cycles long. And so we're going to talk about which cycles and how many cycles and where in the test the cycles are we store and things like that. We're going to talk about test termination. And test termination can be different things. It can be when the specimen is in two pieces. It can be when the specimen is cracked and no longer able to contain the full load. It can talk about when there's a stiffness change in the specimen. Composite specimens, we're talking about metals. But the idea is that in other material categories, we might have stiffness change that isn't shown as a crack or as a change in two pieces of the specimen. We're also going to touch a little bit on environmental controls. Really, I'm just going to talk about different ways to control the environment, not so much details about that. To review, okay, this is a servo loop, a PID control loop. This is what all of our servo-hydraulic MTS machines use. Generally, we close the loop or we use as a feedback signal the LVDT or the stroke or the extensometer or the load cell. Those are shown in the bottom right-hand corner. That goes to a summing junction where it's mixed with the command, one is subtracted from the other, to determine the error signal. The error signal then goes to the valve driver, which then changes the servo valve and moves the actuator to get rid of that error signal, to minimize that error signal. If we're commanding a sine wave, we want the feedback signal to look like a sine wave. It might be a little bit delayed in time, but it's going to look like a sine wave. The next thing is that we talked last time about PID values. One of the questions was about PID values. And the idea is that PID values are applied to that error signal before it gets to the servo valve. So above that valve driver, that's where the PID values get applied to the air signal. We also talked last time about compensation. So if you're not hitting your end levels in a cyclic kind of test, one of the ways to fix that is to lie to the system. If I wanted to go to 10 and I only got to 9, maybe next time I tell it to go to 11 in hopes that it gets to 10. And we can do that in an automated manner with computers. So the compensation is applied to the command side of things. Finally, there's a whole bunch of signals that are a mathematical combination of a real signal like extensometer load cell or LVDT and maybe another signal, or maybe just a mathematical formulation from those. For example, stress, okay, is force divided by area. So if you know the area, you can command a stress signal and have a stress calculation feedback as long as you got a good force signal from the load cell. We don't have to use one of the physical signals directly. We can use one of the physical signals in conjunction with these other mathematics in the modern controllers. All right, let's get into the nitty-gritty of the control mode. In HCF, high cycle fatigue, it's usually load or stress control. If it's load control, it's pretty simple. You're using a physical feedback signal. If it's stress control, you're doing a calculation someplace, and you're looking at the stress calculation. Generally, we're talking about a constant cross-sectional area. If you want to compensate, or if you want to correct for a changing cross-sectional area, we all know there's a plus ohms ratio, so if you pull on something, it gets thinner. And so the idea is you could theoretically calculate what the cross-sectional area is based upon the length change, the strain change, and you could then do more of a true stress calculation. But generally, to make things easy, we talk about a constant cross-sectional area or an engineering kind of stress calculation. The feedback is a load cell. The stress signal can be calculated. We rarely do a true stress or a temperature-corrected stress control. Again, when you heat things up, they get bigger. So if you heat up a specimen and do your HCF testing at elevated temperature, you're going to have a larger area slightly than you did at room temperature, and you probably measured the area at room temperature, but you're going to run the test at elevated temperature. But that error is very small. And so generally people ignore it. And if we do compensation on this stuff, we usually do a very simple compensation like peak valley control, which really just changes the peaks and the valleys. It doesn't care about the shape of the wave. It doesn't worry about, does a sine wave really look like a sine wave, or does a triangle wave look like a triangle wave? It just worries about the peaks and the valleys. On the low cycle fatigue side, it's usually strain control, and it's usually total strain control, meaning that we're measuring a distance between the extensometer arms, and we're keeping that distance, the peaks of that distance and the valleys of that distance constant. We're usually talking about engineering versus true strain, so we're not worried about the instantaneous gauge length. We're worried about the original extensometer measured gauge length, the original engineered gauge length. It's usually not plastic strain or true strain control. It's usually just extensometer or total strain control, engineering strain control. Oftentimes we just use the extensometer to control it, and the extensometer is often calibrated in strain units, not in length units. In reality, the extensometer is in length units, and there's a predefined gauge length. So anything calibrated in strain units includes that predefined gauge length. So if you put the extensometer on at one temperature and it heats up, those arms are going to spread apart. And so your original gauge length is no longer what it was. I mean, your new gauge length is no longer what it was originally. And that means you might have some error in there. And so you have to figure out if you're going to correct for it, or if you're going to ignore it. Some people have to correct for it because the standard says they should, and other people don't have to because they don't need to in their lab. Usually we're talking again about simple compensation. Peak valley control is what MTS uses, which is just a change in the amplitude, not a change in the shape of the wave. We start talking about end levels and frequency and wave shape. We're going to get usually in HCF and LCF, we only ask for two numbers, a max and a min, or an end level 1 and end level 2. When we start to put hold times in, we start to ask for more information. But generally, you're interested in just two values, a max and a min. Sometimes people ask for means and amplitudes, and you can design a test that asks for a mean and an amplitude rather than a max and a min. You can also ask for things like a max and an R ratio or things like that. In HCF, the idea is just to pile cycles on the specimen. Just make it go fast enough so you can get things done quickly. Usually there's like I said, usually there's no hold times in HCF. And so you're just running the test at 10s or 50s or 100 hertz. Some of those tests on various ultra high frequency machines run at 1,000 hertz or so. The waveform fidelity is rarely important. We don't really care if it's a sine wave or a ramp wave. We can run whatever is easy, and usually at the higher frequencies, sine waves are easier. And because there's no plastic strain in an HCF test, or generally there's no plastic strain in an HCF test, there's no rate effect, so the specimen doesn't heat up at all. On the LCF side, we sometimes have advanced waveforms, and so we're interested in things that mix and match different damage methodologies or different damage mechanisms. So there might be a creep fatigue test, and the creep fatigue test might have some hold times at the peak load to allow creep to happen. And in those cases, you have a more complex wave shape. And the other thing that's going on inside of low cycle fatigue is that there's often strain rate dependence after yield. And so most LCF tests yield during each cycle. And so the rate of the test or the frequency of the test is usually important. If you run the test too fast, and I know this from experience, the specimen gets red hot, and that's usually not a good thing because that changes the temperature of your test and everything else. Sometimes we do weird stuff in LCF like plastic end level control or plastic strain rate control, which is really complicated on a servo hydraulic machine because there's no plasticity until you yield. So you're going infinitely fast until yield, and you slow down and run a constant rate, and you go infinitely fast until you get a compressive yield. You slow down and go at the desired rate. That's a rare situation. I also want to talk about wave shapes. There's a whole bunch of different wave shapes available in most of the MTS equipment. Sine, true sine, sine tapered, true sine tapered are among others. The difference between sine and true sine is that sine generates a command from end level to end level. So in this case, the gray curve on the left-hand side is the sine wave shape, whereas the blue one is the true sine wave shape. Sine goes from end level to end level, and so it counts a cycle as from one end level to another end level back to the first end level, whereas true sine goes from mean to mean. So it counts a cycle from mean to the first level, then down to the second level, then back to mean. Same thing is true for the true ramps and the ramp wave shapes. This makes a difference when you're starting to count cycles, and this makes a difference when you're starting to look at peaks and valleys. It especially makes a difference when you're starting to think about noise on your feedback signal and where in the cycle the peaks and valleys happen. It makes it pretty easy to find the peaks and valleys when you're talking about true sines and true ramps. It's sometimes trickier to find the valley when you're talking about a regular sine or a regular ramp, because that minimum can sometimes show two valleys rather than a single valley. Another thing that's interesting is that when we start adding hold times into the wave shape, we start to get changes in our feedback response, meaning in our load versus strain or stress versus strain signal. On the upper left-hand corner, we got a triangular LCF wave shape, command wave shape for strain. And in the upper left-hand corner, we have a normal hysteresis loop. The idea that starts, in this one, if you start at 0, 0 at the origin, you go up to A and then B at the top right-hand corner, then you come down to D at the bottom left-hand corner, then you go back up and start again. In this case, the cycle is really from mean to mean. When we get to the bottom side of this plot for an advanced LCF test with a hold time either at max or at min or both, this one shows at both, we're going to get some load drop because there's going to be some relaxation normally in an elevated temperature test that has this kind of wave shape. And that shows up in the hysteresis loop as a drop in load at the peak load and the peak strain, and a increase in load at the valley load and the valley strain. And you see that as those flat corners on that hysteresis loop. Let's talk about how you make these commands in one of NTS's applications called Test Suite. So Test Suite has a bunch of different ways to generate commands, generate wave shapes. On the left-hand side, we're showing a really simple HCF kind of wave shape with a true sine command, and it's running 1 million cycles or more, and it's doing peak valley amplitude control. And down at the bottom, we see an absolute end level 1 and an absolute end level 2. And up near the top, we see a frequency of, I think, 10 hertz. On the right-hand side, we see a more complex wave shape. And this wave shape has 5 segments. It's a ramp to mean. It's a ramp from mean to the max, a hold at the max, a ramp from the max to the min, a hold at the min, and then a ramp back to mean. And this is a slightly longer wave shape also. It looks to be 4 seconds long, whereas the first one is 1/10 of a second long. This one runs without any compensation because this is a relatively slow wave shape, because 4 seconds is slow. And this is running an extensometer control. This extensometer is calibrated in length units rather than strain units. All right, let's talk about some data acquisition stuff. Some data is more important than others. It's sort of like that old George Orwell book about some pigs are more important, or some animals are more important than others. The pig said, right? So the idea is that some data is really important to get right, and other data is less important to get right. And there's multiple purposes for the data acquisition in addition to cycle count. Cycle count is probably the most important thing in both LCF and HCF. But there's other things you need to do and collect, and at least in LCF. And you can use the data for a variety of purposes rather than simply to analyze the test. You might need to monitor the material response as a function of cycle count. And so did it work the same in the beginning of the test as it did at the end of the test? Was it the same mechanisms with the same response, with the same behavior? How do you add up damage, right? As part of that question. You might want to monitor material response as a function of cycle period. If there's a hold time, how does the load relax during the hold time? And you can think about that as during the same cycle, and you can also think about that as how does it relax in the first cycle versus how does it relax on the 10th cycle, the 100th cycle, the 1000th cycle. You might want to characterize the response. You might want to say, this work hardens over the first 1000 cycles and then it stabilizes, and then I can figure out a typical cycle, and I can use that to look at all succeeding cycles. Or you can characterize a single cycle, like the hysteresis loop. What is the ratio of plastic strain to elastic strain? Those are the kind of information, those are the kind of things you could do with the information either during the test or after the test. Once upon a time, the idea is you had to take enough time data, because once upon a time, the only kind of data that existed was time data. You took a lot of data in time, and you figured out where the peaks and valleys were from that time data stream. And in that case, you had to take a large number of data points per cycle so that you could find a value close to the peak and close to the valley. Things are a little bit different these days. We can use all the data that's available to the controller, which is usually 5,000 to 6,000 data points per second. And we can search through all the data to find the peaks and valleys. And then we only have to store some data to disk to characterize the hysteresis loops. Usually it's 100 or so data points to characterize the hysteresis loops. But we don't need to take data at bazillion hertz in order to find the peaks and valleys. We don't need to take cycle data at a bazillion hertz in order to find the peaks and valleys. Let's talk more about the peaks and valleys. We need to collect the peak and value of the control and feedback signal, of the control feedback signal. So in other words, If you're running strain control, you need to take peak values for strain data. And it should be pretty boring data. It should be the same value every single cycle. And if it's not, you know your test isn't quite right. You know that there's a problem with your control. We also need to collect peaks and values of the other signals. And so if you're running in strain control for an LCF test, you need to take load or stress data. And that's how you determine, that's one of the ways you can determine failure. You can also understand how things relax. You can understand how things work hard or work soften. That response is as a changing function of cycle is important. MTS has triggers, has time triggers for taking time data, has peak and valley triggers for taking peak and valley data, and it also has delta level crossing or level crossing triggers for taking other kinds of data. We'll talk about that more. The idea is that your trigger sensitivity, what is a peak and what is not a peak, what is just noise, has to be bigger than noise and less than the amplitude of the cycle. And you know, my rule of thumb is usually about a quarter of the amplitude of the cycle. If I'm using the strain data, I know what the amplitude of the cycle is supposed to be. If I'm trying to create a sensitivity for a peak valley load trigger, I got some more problems and I got to guess at things. You should not collect and store every single peak and valley. You do collect every single peak and valley, but you shouldn't store them all. Because in a million cycle test, you don't need a million data points to dig through to make sure it worked right. You need a few. And a few is an eye of the beholder, but it's usually thousands. You should not abandon control with a need for speed. So in other words, if you want to run fast, you should make sure you're still controlling at that fast speed. It's possible that you need to slow it down by 10 or 20 hertz in order to get good control. You should not use the wrong triggers. And so don't assume that the stress peaks occur simultaneously with the strain peaks in a test with holds at the peaks. Your strain peak will have noise during that hold time, and it might pick the peak someplace not near the beginning, whereas the stress will relax, and so the peak really is near the beginning, as this little this dark black line on the plot shows. Cyclic work hardening and cyclic work hardening and work softening. If you guys are not familiar with this, you know how when you're a kid, you took a paper clip and you bent it back and forth? And the more times you bent it back and forth, the easier it got to bend it so you could break it easily. That's sort of a cyclic softening idea. The idea is that on the first cycle, you had to work hard to bend it, and on the last cycle, it was much easier to bend it. Work hardening is a different idea, meaning that the more you work it, the harder it gets moved the next time. It's sort of like straightening out a bent nail. The idea is that it doesn't quite get there the next time until you put more force into it. Grabbing peaks and valleys helps you figure this stuff out. Now let's talk about data acquisition for hysteresis loops. Hysteresis loops are not necessary really in HCF. We know that it's supposed to be flat. You know, if you grab hysteresis loops, it's really just to make sure that there's no plasticity going on, or make sure there's no friction in your system. If there's friction in your system, you might have a different value for loading versus unloading, which makes a hysteresis loop. But it's not energy going into the specimen, it's just friction in the grips or someplace else in the system. So generally in HCF, you don't need hysteresis loops. But in LCF, they're very important. LCF, there's plasticity, and you're trying to characterize that plasticity or that energy going into the cycle on every cycle, going into the specimen on every cycle. Time data acquisition is easy, but it doesn't work for hold times. It's easy because it's been around forever, and it doesn't work for hold times because if you have a long hold ratio to ramp ratio, maybe a 10-to-1 ratio, you're going to get 90% of your data during the hold time and 10% of your data during the ramp time. So 90% of your data is going to be at the peak or at the valley, wherever the hold is, because the load isn't changing much and the strain isn't changing much. And if you want to look at the shape of the hysteresis curve, you only have 10% of your data to do that with. And so there are smarter solutions for taking hysteresis loops with hold times in them. Oh, we already talked about this one. All right, here's the smarter solution. Multiple triggers for data acquisition. The idea is if you have time data, it would look like these blue dots in the bottom right-hand corner. And that's good, but most of your data is at the hold time, right? If you also take level crossing data, and in this case, it could be either time or displacement, time or extensometer, load or extensometer level crossing data, you would get other data points. And those other data points would help you fill in that hysteresis, it would help you fill out the area that's loading or unloading and not have all the data points at the peak. The idea is level crossing is a generalized version of timed acquisition. In timed acquisition, you're taking data whenever the clock changes by a certain amount. In level crossing data, you're taking data whenever something else, load or strain or something else, changes by a certain amount. So the next question is, which cycles are we going to store? As we saw earlier in that work hardening, work softening stuff, things happen at the beginning of the test. Things happen and then they settle out, right? So you're always going to take some cycles at the beginning. And things happen at the end of the test when the specimen is dying, when the crack is growing, when the specimen is breaking. So you're always going to take some cycles of data at the end of the test. The middle of the test is the important part because that's sort of the standard average typical kind of cycle. And so you got to take some cycles in the middle of the test. Problem is you don't know where the middle of the test is. You can always create a circular buffer, meaning always keep in memory the last 20 or 100 or 200 cycles from the test. And as a new one comes in, you can throw the oldest one out. That gets you the last cycles, because when the test ends, you have a bunch of cycles of memory that were the most recent cycles. And the beginning ones are pretty easy to store because you can just store the first 100 cycles. But those middle ones, you don't know where the end of the test is, so you don't know where the middle of the test is. And so you have to store data periodically. And periodically can be every X number of cycles, or it can be X number of cycles per decade. Per decade means, per factor of 10. So you could sort 20, 30, 40, 50, 60, 70, 80, 90 in cycle 100, and then cycle 200, 300, 400, 500, 600, 700, 800, 900, and 1,000, then 2,000, 3,000, 4,000, 5,000, etc. If you remember last time, all this amplitude versus cycle, these SN curves or strain life curves, were all on a log-log plot. And so by storing data logarithmically, it's sort of evenly spaced on that plot, meaning that you can get a good idea as to what you can get a good idea as to what cycle count was the closest to the middle. And you don't have to save that many as a result. If you do 1 million cycles and you're storing cycles 10 per decade, you only get 60 cycles. Some folks, need to prove that every cycle was good and every peak and valley was good. In those cases, you're going to get a big data file. Bits are cheap these days. You can store it, but it's really hard to analyze, and so I don't suggest it. There's a way in MTS's application called Test Suite to choose which cycles to store. On the bottom left-hand side of the screen, we can talk about that starting in any cycles. In this case, it's going to store the first 100 and the last 100 cycles. And then underneath that Select Cycles button, there's another pop-up window that says you can store cycles per decade, or you can store every nth cycle, which is linear storage. You'd usually pick one or the other, but there's checkboxes, so you can pick as many as you want. In certain instances, some of the questions came up last time about fatigue crack growth. You want to store data whenever something changes. In this case, maybe when the crack size changes. We don't usually worry about that in low cycle and high cycle fatigue, but we might look at the peak load and store data whenever the peak load drops by some number in a strain-controlled LCF test. That might get us data close to the crack initiation cycle or something else. So I was talking about test termination, or how do you know the specimen is broken, or how do you know the test is done? In an HCF test, that's pretty easy, because in an HCF test, you can't hit your loads if the specimen is broken, and your displacements go to large numbers. And so it's pretty easy to put a limit detector or some other kind of detector on a machine that's running an HCF and load control. You have to be really careful sometimes, because that actuator will move down, and if you have something, if you're running a test with something in a furnace and your grips are bigger than your furnace is, that can be very bad if it runs down pretty hard. So the idea is you have to be able to catch that relatively quickly. Usually any kind of metal specimen that goes more than a quarter inch or 6, 7, 8 millimeters from its initial position is broken. And so you can assume that it can shut the test off and turn off the hydraulics and clamp the actuator in place or something else. LCF's a little trickier, because in LCF you're trying to move between two positions. And even though the specimen is broken, it can probably still move between those two positions. It can probably still follow the extensometer and hit those two extensometer values. Or, it will, in one case, it'll compress the fracture surface faces, which pisses off most guys that want to look at them after the test. And in tension, it will spread the faces apart and move the extensometer arm of the part to a certain value. So we have to do something different in LCF. Usually what we do is we look at the loads, the peak loads, and when the peak loads drop off from some stable cycle, and stable cycle is a fuzzy word, then we shut the test off. We say it's broken now. And the real question is, which cycle are we going to claim is stable, and how much should it drop off before we shut the test off? Those are the kind of parameters that are necessary in the LCF test to determine this kind of failure detection. Usually, you can catch the specimen before it's broken in two pieces when there's a crack in it, but it's usually a bigger crack. It's usually a quarter of the way through. So it's well after initiation, but it's not fully broken sometimes. We can also do things like look for stiffness changes or other stuff like that. We'll talk about a little bit more about that in a minute here. Like I said, there's a problem if we don't really stabilize. If it's always decreasing, if it never stabilizes, meaning it doesn't always work hard, but sometimes it continuously works often. It's hard to claim that there's a stable cycle in there someplace. And if you can't declare a cycle to be stable, it's hard to look for a decrease from that value. MTS provides a couple of different ways of finding the stable cycle. One of them is when the peaks and valleys, when enough peaks and valleys are between this region, then call the last one the stable cycle. Another way to determine is just declare that cycle 100 is going to be stable because everything happens before that. So we'll just remember what happens in cycle 100 and then compare everything else to it. There's not a good answer as to what you should try in your specimens. Depends on the behavior material. Let me get on to the next one here. All right, stiffness change. There are some materials, metals or composites, that show stiffness change when cracked in tension. The idea is that there's fibers, there's other things in those metals, and so the specimen might not break or crack, but parts inside it crack. And the parts inside it that provide the stiffening or provide significant load carrying ability crack. And as a result, the stiffness of the specimen as a whole changes, which is the same thing as the load dropping off on the peak, but it's more than just the load dropping off on the peak. We can constantly monitor the stiffness of the specimen because we can constantly monitor the hysteresis loop. And we can do a linear regression from the hysteresis loop to figure out if the stiffness has changed, if the modulus of the material has changed. And if the modulus has changed by a certain amount, we could shut the test off. The idea is that this is useful because the modulus is always positive and the stiffness is a relative drop to the initial value, 10% drop or 20% drop. And as a result, in certain situations, this is very useful. Let's talk about a different topic now. Let's talk about restarting tests. In HCF, that's not a big problem because in HCF, you're always elastic. So when you stop a test, it follows the elastic line back down to 0 or back down to its initial starting point, essentially. Whereas in LCF, that's a big problem because when you stop a test, it may not have been compressed back. Maybe you've only done the first half of the cycle, so you've deformed it in tension, but you haven't squished it back down in compression yet. And if that's the case, you don't want to put two half tension cycles on top of each other, so you don't want to start it out in tension again. You want to start it out going in compression. The idea is that you can't, when you restart a test, you have to know where it ended. And it's useful to be able to finish the cycle before you stop a test if you can control how the test ends. You can't always control it. Sometimes power goes out, sometimes something bad happens, but the idea is that if you can control it, you sort of want to finish the cycle before you start, because then you can start it from a known state. Another thing that's pretty important is if you take the specimen out of the grips partway through the test, you got to put it back in the same way you found it, right? It's like your mom used to tell you growing up, you got to put things back where you found them. So the idea is if the extensometer arms are not reading 0 because there's some plastic strain on the specimen when you stop the test, some residual strain on the specimen, you got to put them back at the same distance apart and reading the same value. Otherwise, you're going to get a bump in your force signal, the force response. Because you have some additional plastic strain in that test that's not accounted for. So the idea is that you need to put things back where you found them also. One of the pieces of the MTS templates that we create for Test Suite helps you do that. It remembers where it was, and it tells you to put the arms back with this value and put the signal back with this other value. And if you're doing this at high temperature, it remembers it both at high temperature and at room temperature. And that makes things a little bit easier. Let's talk about environment, high temperature stuff. This is an example of a lab with a bunch of furnaces. And so one of the environment things is furnaces, is hot or warm. So furnaces are ovens. Hot meaning 600, 700, 800 degrees Celsius or 15, 16, 1700 degrees Fahrenheit. Warm is more like 1000 Fahrenheit, 300, 400 Celsius. It can be corrosive. There's salt fog, salt water, hydrogen sulfides, coating the specimen. There can be hydrogen gas around the specimen. There's a lot of work right now with for green gas, natural gas with some amount of hydrogen gas inside the natural gas, and pressurized. And people are interested in, can our pipes handle that? Are our pipes going to be hydrogen embrittled by this? There's cold environments. They can be cryogenic cold like space, or just Arctic cold like Minnesota. There's wet and biocompatible stuff. So there's knees and hips and stents and teeth that go inside, 98-degree liquid that is fake spit or fake blood. And then there's inert. There's things that can't endure oxygen. And as a result, they are either vacuum-oriented or they are vacuum-oriented and backfilled with argon or something like that. We saw this picture last time, 2 weeks ago. This picture is a vacuum chamber from a very early MTS system. There's induction heating to make things hot. Induction heating uses magnetic fields around them, in this case, a copper wire carrying a current. And that copper wire creates a magnetic field. The magnetic field couples with the specimen gets red hot. And you can change this very quickly because there's really nothing other than the specimen that is hot in this case. The copper coil or the copper wire has water running through it, so it is not hot, but the specimen next to it is. There's this inert or vacuum chambers with gas. Those are tricky because you need to put the extensometer in there with everything else. So it tends to be very nasty for any kind of extensometer or any kind of transducer inside the furnace or chamber. More examples of inert or gas furnaces. There's some cryogenic systems. Those are also tough on extensometry because again, you have to put the extensometer in with the system if you're going to do that. The cryogenic systems are usually liquid nitrogen oriented. You can get a little colder with liquid helium, but that's not, it's not cheap. So liquid nitrogen is usually where things bottom out. And then there's hot systems, and hot can be compressive, tensile, both, that kind of thing. Then there's complicated things like special planar biaxial systems, which pull on the specimen in 4 different ways. It's a cruciform specimen, not a typical low cycle or high cycle fatigue specimen. And there's autoclaves, which have pressure inside there with the specimen. And so there's a tendency to change the load on the load cell due to the pressure inside the autoclave pushing up on the pull rod. And so you have to correct for that kind of stuff in these kind of situations. Oftentimes, with compressed steam or gas, you also have to worry about what does that do to the extensometer and how does that affect the results. Grips have to go inside there. Inside furnaces, there can be multiple zones. There's direct heating or induction heating. Direct heating is when you plug it into the wall, so the electricity goes right through the specimen and makes it hot. It's usually not as simple as plugged into the wall, but the idea is that you can use current going through the specimen to make it hot. For wet systems, you can build it upside down, and so you can put the actuator in the air and use gravity as your friend to hold the liquid into the bucket that you're going to test the specimen in. Let's look at a couple of images and then we'll be done. And then we'll take questions. So the idea is that we need to get information for every LCF and HCF test about the specimen so that we can calculate things like stress and strain. So we might need things like, we first need to know what kind of specimen it is so we can calculate stuff. Use a pi r squared or a width times thickness or some other kind of calculation. So there's some questions that we ask about the geometry. Then we ask about the material. We ask about the modulus of the yield strength. I'll talk more about that later on. And then we ask about gauge length and diameter and things like that, width and thickness and so on. We can use those modulus and yield strength to calculate other things. We can estimate what the load is if we're going to go past yield, and because the yield load is going to be bigger than the yield load. And we can estimate from the modulus and the yield strength what the other signal would see when we command this signal on one of those channels. We also do this in both LCF and HCF. We want to make sure the test is going to run before it runs. And as I said earlier, there's no guarantee to this, but the idea is if you measure something you already know, and that measurement turns out correctly, then the test is probably set up right. You've got your extensometer attached correctly, you've typed in the right parameters for the geometry, you are controlling in at least one control mode. And if that's the case, you measure something you already know. In this case, we're going to measure the modulus. And if the modulus turns out close to what you thought it was, then you probably are going to have a good test. It doesn't test everything, but it tests most things. And I usually call it a sanity check. It makes sure the machine is not insane. It'll tell you whether your calibrations are good enough. It won't tell you if they're perfect, but it'll tell you if they're good enough. It'll tell you that everything is attached correctly and so on. And that's usually a starting point. I make sure I run this sanity check on every test I do before I run the rest of it. The main control screen can be something simple. This is a simple HCF test. The top line of this dialog box has 3 buttons. Those 3 buttons are for adding in parameters, okay? Let's go back to this one here. So the top 3 buttons for adding parameters. The first button is for end levels or command parameters. The second one's for termination parameters. The third one's for data storage parameters. And then we got some buttons for measuring the modulus and running a test, and some buttons for reporting. The screens look something like this. There's some plots and tables and summaries. Other tests might be more complicated. This is a trapezoidal, elevated temperature trapezoidal test. So there's a lot more buttons here because there's a lot more stuff to do. There's temperature parameters, test parameters, including end levels and ramp hold times. There's termination parameters, data storage parameters. There's extensometer verification, strain measurement, modulus measurement, strain measurement during the heating stuff. There's ramp to temperature. There's the fatigue test itself, the LCF test itself, and there's reporting. There's also someplace in here. There's the ability to get it back in the place you found it. So there's a reset or reattach extensometer idea in most of these tests. One more topic here. The idea that one of the questions that keeps me awake at night, okay? We've talked a lot about plastic strain and elastic strain in an LCF test. There are multiple ways of calculating plastic strain and elastic strain. One way is to measure the width of the hysteresis loop. Another way is to measure the peaks and valleys of load and stress, or stress and strain, I should say, stress and strain, and using the modulus, figure out how much is elastic and how much is plastic. Those are two different calculations, and they result in slightly different answers, primarily because the modulus is not always exactly what the data shows. And as a result, we can report both of those, and we do report both of those. One is taken from peak and valley data. The other is taken from timed and level crossing data. Finally, we've been talking totally about constant load amplitude or constant strain amplitude kind of tests. There's a whole nother world of fatigue that is variable amplitude. And it's used primarily for simulation of loads on components. And there's a bunch of ways to identify how that damage is accumulated and which cycles are important and which cycles aren't important, and how to simplify your commands to only apply the important cycles. And we're not going to talk about that today. Lastly, there's a bunch of standards we've been talking about. We've been talking about some ASTM standards, E646, E466, E606, some ISO standards. That's an LCF standard from the ISO group. Then there's a bunch of corporate standards also. GE Aircraft has their own standard, which is very similar to the E606 that goes beyond it, for doing strain-controlled low-cycle fatigue. A lot of that work is done at elevated temperatures. Allied Signal has another specification, similar. Now we can have questions. Sorry about that.
That's great. Thank you. That was a lot of information, and we're ready to answer some questions. Our first one is, how do I do a constant strain rate in low cycle fatigue?
So the quickest way to do a constant strain rate is to do some math. You can do some math either before every test, or you can rewrite the MTS test to do the math for you. But the idea is you can apply your end levels and type in your end levels, type in your strain rate, or use your end levels and your strain rate to figure out what the frequency is. And if you change the MTS test, you can just type in the rate and the end levels, and it'll figure out the frequency for you. And if you do the math ahead of time, you use the rate and the end levels to calculate the frequency. You know that you're going to go between the min and the max twice. And so the total excursion is going to be twice the difference between the min and the max. And you can apply the strain rate to that to figure out the frequency.
Awesome. All right. Here's another. Are capacitive extensometers good options for high temp fatigue testing? What are the drawbacks?
Capacitance extensometers work well up to about 500 C. I don't think they work much higher than 500 C. I'm old, and when I was younger, I used capacitive extensometry. it was very fragile at that time. It's much more robust now. When I say fragile, I had to take it out of the furnace, put it in the desiccator, and keep it in the desiccator between the times I was using it, things like that. The idea is that today it is a robust solution. It will work. The primary issue with any kind of extensometry and LCF is you're only going 1 or 2% strain. And so your excursion, your displacement is relatively small. And I suspect that most capacitive extensometers fit right in that range. So they can be used.
All right. During a test of a metal fastener, high cycle fatigue, startup will overshoot the max load in the first few hundred or thousand cycles. How to avoid this?
Detune it a little bit. That's one thing. Because if it overshoots, it's overshooting because the error is not being correctly compensated by the PID values, right? So you can detune it, meaning lower the P value by 10%, is my guess, and lower the I value by 10%, lower the D value by 10%. Or at least better tune it, let's put it that way. And if you better tune it, I think you're gonna get rid of that overshoot. Any kind of load control, every time you change the geometry of the specimen, every time you change the material of the specimen, you might want to retune it. Load control is one of those goofy things, is that it's all based on the stiffness of the specimen. And so if you have another specimen that's a different stiffness, you're going to need different tuning parameters.
All right. How can we ensure that inputs of a test are outputted in our data files after a test?
That's primarily, if you're talking about test suite, that's primarily a reporting function. And so if you're inputting those things into test suite knows them. And so now you just have to make sure that test suite regurgitates them back to you in the reporting software. It's if you're not putting them into test suite, then they got to be stored someplace, either a lab notebook on your desk with your handwriting on it or something else. And then then you have to get them into your report some other way. I think that's best way to talk about it is that we should talk more about reporting functions in test suite for that.
Great. Okay, how do we turn off the hydraulics upon break detection? Is there an option in test suite for this?
Yes, there's an option in both the LCF and the HCF standard MTS templates that throws an interlock when it thinks it's done, and so you can turn on that option, and that's it's an option, right? You can in the termination parameters. One of the termination parameters is a checkbox that says turn off the hydraulics when the test terminates. And so first it stops the test, then it throws the hydraulic interlock to stop the hydraulics. So they're not running all weekend long or something like that. If you only got one machine and you run in the middle of the night, kind of thing. Remember, if the specimen's broken, it'll sort of, the oil will drain out of the actuator, and so the actuator will move down if you've got a base plate mounted actuator.
All right, not sure I understand this one, but hopefully you do. What is the acceptable recommended delta value for the desired versus actual response peak valley measurements? What would be the corrective measures to reduce this gap within the allowable limit?
Yeah, so rule of thumb is you want to hit within 1% of your range. So you want to hit 99%, between 99 and 101% of your desired values. That's my rule of thumb, at least. It's one of those eye of the beholders, or how many angels on the head of a pin. But the idea is that should be doable. And so then the question is, it's not doable in every single cycle. It's doable after things after the compensation learns and after things stabilize and stuff like that. So the first cycles might be wrong. The first 10 cycles might be wrong, but you should be able to get there sooner or later. And so part of it is get your tuning parameters down. In strain control, they don't change much from specimen to specimen. In load control, they change a lot from specimen to specimen because the stiffness changes a lot from specimen to specimen. For a given specimen size and a given specimen material, those 5 specimens will all behave the same, so they can all use the same tuning parameters in load control. But But the idea is that if you change to a different size, a different diameter specimen, you're going to have different stiffness, so you have to change the tuning parameters again. So the first step is get the tuning parameters down. Second step is turn on compensation, the peak valley control or some other compensation, because whatever tuning doesn't fix, that will fix. And finally, there are some compensation parameters. There's one parameter that says how much to fix every time it fixes it, and you don't want to overfix it because you start to yo-yo around the right answer. You'll overcorrect, then undercorrect, then overcorrect, then undercorrect. So you don't want to fix more than like 40% of the error on every time you fix it. But the other piece of that is, the other parameter in the peak valley control is something, I don't remember the name exactly, it's either sensitivity or something else. But the idea is that when to stop fixing, when is close enough, when is close enough. And you might have to lower that value in order to get within that 1% of the desired value window.
All right, I think we have time for one more here. In HCF, my force amplitude response to the command tends to vary from sample to sample. What settings should I change to keep the force response accurate across my samples?
If they're all the same material and all the same size, then your PID values shouldn't need to change. If they aren't the same material and aren't the same size, or if there's variability in the stiffness of those specimens, then your PID values might have to change. And that's a pain in the butt if you have to change them for every single sample you got. I would try a lower frequency to see if they still change, meaning that you might be in the world of I'm giving up control for speed. And so that was one of those don't do this kind of things. So first step is to check your PID values and check your stiffness. Second step is to maybe check your compensation. Okay, maybe it's overlearning, underlearning, overlearning, underlearning kind of things. So make sure it's not at correction of 80% or something. That's the best I can say right now until I see more.
All right. Well, I think we're going to wrap up here. Thanks again for sharing your fatigue testing expertise, Dr. Schwarzkopf. And thank you to our audience for their attention and interesting questions. As a reminder, a recording of this and the first webinar in the series will be available online within the week, and you will receive an email notification when they're posted. Thanks again for attending the webinar, and we hope to see you at future events. Thank you.